All right, so the other day I introduced the differences between the two major types of AC motors, so synchronous motor and the induction motor. All right. The name sort of says what the differences are. So the synchronous motor, the big deal is that the rotor and the field are moving at the same speed. In an induction motor, the rotor current is induced. Okay. And so we'll kind of go through those details. So basically, here's the picture of them, right? So on the left, all right, what I have is my two-pole induction motor. And on the right, I've got my two-pole synchronous motor. Now, I mentioned this the other day. So any motor can be both a motor and a generator, right? So if it's a motor, what is it doing fundamentally in life if it's a motor? Turning electrical into mechanical, right? So I'm creating mechanical work. If it's a generator, it's taking mechanical work and converting that into electrical power, okay? The synchronous machine, and so I use the general term machine, right? They're electric machines. In general, the machine, to say that it can be a motor or it can be a generator, either one can do either function. But in general, the most common thing historically for a synchronous machine has been to be a generator. All right, that's basically a large machine, hundreds of megawatts. The motor, the induction machine, his primary job has historically been to be a motor. That is not to say that he couldn't be a generator. He can, and many wind turbines are induction machines. All right. The synchronous motor is much more commonly now becoming a motor. All right. It's harder to use as a motor for reasons that we can kind of talk about a little bit as we go through today. Okay. All right. So in this case, just looking at those pictures, these are both two poles, right? What does it mean to say that it has two poles? What is it? Yeah, the field changes its direction every 180 degrees, right? So 180 degrees physically. So excuse me. So if I looked at phase A on this guy, right? Phase A would have a field that points in along the top half of the rotor, and then he would flip his direction on the other side. Okay. And he would point out on the other side. All right. So we've gone through that plenty of times. I'm not going to go through that too much more. All right. And notice here, I called these AS, BS, and CS. All right. What's S versus R? Stator versus rotor. Okay. Pretty straightforward. Again, I think you guys are getting those basic concepts now, but looking at these two pictures here, again, these are cross-sectional cuts that we through the middle of this thing, right? What's the difference between the rotor side right here on the synchronous and the induction? What's the difference there? Well, yeah, synchronous has that F coil, right? And it only has that one coil on the rotor, all right? What about on the induction machine? It's a three-phase winding. Now, very often it doesn't actually have a three-phase winding. All right. What it has is a cage, but it acts like it is a three-phase winding. Some induction machines really do have a three-phase winding. Either way, it acts like it has a three-phase winding, so we're going to model it that way. Okay. All right. So those are our two pictures. Now, one question I'm going to jump to this, and I'm going to jump back for a second. The differences in the rotor in the two cases, right? So if I were to take the rotor out of the synchronous machine, what I would have is something, what I've got over here. So this would be the synchronous, and this would be the induction. All right. In the synchronous machine, so basically these slots right here, these are windings. All right, so there's windings all along that thing. So wherever I see a slot like this, there's a winding. And I get current into those things by basically applying a DC voltage supply to what I call slip ring. So basically there's a set of brushes that touch these pieces of carbon right here, and a current would flow in, then enter these windings, and then flow back out. And this is that field current, I sub F. All right, that's how that guy works. So there is a direct connection to that thing. There is another type of synchronous machine. If you go into a Tesla, any kind of electric vehicle or whatever, they also have synchronous machines. But instead of a field winding, what they have is magnets, right? There's magnets inside of that rotor, okay? That would totally work the same, right? What that field winding is doing is you put a DC current into it, and it makes this rotor look like a magnet, right? Effectively. So I could do the same thing without having the slip rings if I put magnets inside the rotor. All right, so that is also a feasible thing to do. All right, we'll look at that towards the very, very end. This guy on the left here, this is what an induction machine looks like. So I have a three-phase set of windings on the stator. Okay. Those windings are supposed to be sinusoidally distributed, right? And that's what I've been saying all along. In other words, sinusoidally distributed, meaning if I looked at phase A, there would be a lot of windings right here at 0 degrees. And then they would decrease as I went in both directions away from 0 degrees. Now, in reality, that's pretty, from a practical perspective, really hard to do. All right. What you see is like when I brought that winding belt in before, right? What you have is windings that are held up in slots. And so you distribute them in such a way with those winding belts that they sort of look sinusoidal, and you see something like this. You look at that picture there, you can see there's windings hanging in slots in the iron. Okay. So there has to be slots to kind of hold them in place, or else they'd fall. Okay. So the rotor on this guy, if you notice, there is no connection to the rotor at all on the left. No, in other words, no connection electrically. So what you're looking at is the middle piece here. This is what I would really term to be between here and here. This is what I would term to be the rotor. Okay. And then I have these parts here, which is really just a shaft. All right. And somehow there would be bearings on those shafts to hold this guy in place. Okay. And I meant to bring in a rotor. I've got it sitting in my office. I didn't bring it up. I'll just bring it on Wednesday. All right. The important thing is, if I look at this guy right here, these things, these black lines right there, what those are bars. They're bars of, in small machines, this one here would be a small machine. When I say small in the context of its horsepower rating, right? Those windings might be aluminum. Okay. If I had a nice big motor, 100 horsepower or something like that, it's probably a copper bar. All right. And so what's happening is, as this rotor spins, we induce a current into the rotor. Okay. And sometimes this thing here is called I don't know if I'm going to spell the word right, squirrel cage rotor. All right. Basically what it is there's a cage of bars. And if there was no if there was no iron in the rotor, you could imagine, I guess, a squirrel running around inside the cage, I guess, like a hamster on a wheel. I think I've always imagined that's where the term came from. All right. All right. I don't know. Somebody at GE in 1910 came up with the term, I guess, or something, right? We'll find out. All right. So those are the big things. So the induction motor was the big invention by Tesla. Really smart idea, because I don't have to actually touch the rotor to push any current into this rotating piece. Synchronous machine, I got to push a current into the rotating piece. All right. A DC motor, as we'll see, I got to push a current into the rotating piece. Induction motor, I don't. And so this guy is the workhorse of the world. All right. And then you go into any factory, any kind of plant, any kind of, if you look in a building like this, all the fans and the pumps, all induction motors. They're nice and rugged. All right. They don't really wear out. Okay. All right. So key difference. In both cases, I have a three-phase set of windings on the stator. I hook them up to a three-phase voltage source. I get a three-phase set of currents. Okay. What does that do when I put a three-phase set of currents onto these windings? What's the primary thing inside? If you don't remember anything else about all the details, the magnetic fields and reluctances and all that kind of stuff, what happens if I put a three-phase set of currents into these windings? 3 windings, 120 degrees spatially apart, get currents 120 degrees temporally apart. What's that do inside the machine? the field starts to rotate. It creates this mechanical field that rotates around. All right. And that, if it's a 60 hertz grid, so in other words, if V of t is V cosine omega t, right? So usually that's how we write VA. If I have, if this omega is 2 pi 60, what's the frequency at which that field rotates? 60 hertz. It just moves around at 60 hertz, just rotates around at 60 hertz. All right. Now, in the case of the synchronous machine, I put a DC current into it. And at what speed do I rotate the rotor in the case of the synchronous machine? Yeah, if it's a two-pole machine, I rotate it at 60 hertz or 3,600 RPM. If it's a four-pole machine, I'll rotate it at 1,800 RPM, and that means the field that it creates will also rotate at 3,600 RPM, right? So the idea of the synchronous machine is I have the rotor speed electrically, let me say it that way, rotor speed electrically equals the field rotational speed. Okay. And this guy is omega, the 60 hertz frequency. And the rotor speed electrically is P over 2 times omega M. Okay. So real quick, if I have a synchronous machine, how can its speed vary? It cannot. All right. For this guy to produce a constant average torque, and that's its goal, it has to rotate at one particular speed. Now, Wednesday, we're going to go back and review that question again real quick because it relates to problem 1 on the current homework. Doesn't mean, so I'm talking about steady state stuff. In steady state, those two things need to move at the same speed. In transient, they might be different, right? We looked at that last week, right? If I increase the power on a generator, right? I push more power into the turbine. For a short period of time, what's going to happen is the speed is going to change, but it's going to come back to the same speed. All right. So these things have to operate at the same speed. All right. Now the induction machine was different. All right. In the case of an induction machine, right, what happened in the induction machine? Well, time t equal to 0, if I put a current into, so in other words, a three-phase set of currents into A, B, and C, that makes the field start to rotate around. Now, at time t equal to 0, if I'm just, let's say I'm starting a pump or something like that, what's the speed of the rotor at time t equal to 0? Before I just, or right as I close the switch to turn on those currents. Speed is 0, right? So the rotor is just sitting there, just flat, right? It's not moving. And then all of a sudden I put a current into the stator windings. That makes a field appear. So that means there's a changing magnetic field passing through these windings here. If I have a changing magnetic field passing through a set of windings, what happens inside those windings? Yeah, induce a voltage or induce a current, right? In this case, those windings are short-circuited, so it's going to make a real current going around those things, right? And if the field is rotating at 60 hertz, the frequency of the current in the rotor is going to be 60 hertz. All right. Now, there was a field that's generated by those A phase or by the windings on the stator, and there's a current induced by the field created from the stator. If there's a current that's induced in the rotor and there's a field passing over it, what happens if I put a current carrying wire into a field? Well, it's going to be the Lorentz force law, right? I'm going to yank on it. I'm going to make it move, right? There's going to be a force on that rotor. So I create a magnetic field. In the case of the induction machine, I create a field. That field induces a current in the rotor, and the field acts on that current to create a torque and to make it move. Okay. Now, as this guy speeds up, the relationship we said Newton's law is J d omega m by dt equals, all right, that's the net torque. right? J d omega m by dt. If I'm operating as a motor, this is equal to the net torque. There's two torques that I typically worry about, right? Which one goes first if I'm talking about a motor? The electrical torque, yeah, because it's the torque coming from the currents that's making this thing move minus whatever my load torque is, okay? So initially, right, what's going to happen is this guy is going to speed up, right? Tau E is going to be, so this, if he's sitting at rest at omega m equal to 0, there's an electrical torque on this guy. Let's just think about there being no load for a second, right? Which there could be. There could be almost no load on the machine. If it's not hooked up to a pump or anything else like that, there's not much load on it. It's a little bit. There's friction from air and stuff like that, but very little, right? This guy's going to speed up, okay? So as he speeds up, then the rotor starts to increase its speed, and the frequency of the current that's induced in there is going to change, all right? Now, if this guy gets to full speed, what's true about tau electrical and tau mechanical? They will equal to each other, right? They'll equal to each other. At that point, if there's no load on the machine, omega m will get to the point where this guy is rotating at the same speed as the field. If he's rotating at the same speed as the field, right? We looked at the video of this last time. If he's rotating at the same speed as the field, then from the perspective of the rotor, there is no changing current passing through the rotor. So there's no current induced, and so there's no torque produced. All right. So basically, those are two ends of the spectrum, right? One end is at 0 speed. There's a 60 hertz current that ends up in the rotor. It gets yanked along to start producing torque. And then at full speed, there's no current in the rotor and no torque production. Where we operate is somewhere in between. All right. So we're gonna go through that all today. All right. Questions about that basic principles? And we do a lot of derivations, but those are the basic principles by which this thing operates. Okay. All right. All right. So in the case of the synchronous machine, they always in steady state always have to be locked to each other, in synchronism with each other. For an induction machine, if I am producing torque, what must the speed of the rotor be relative to the field? If I'm actually making torque, what has to be true? This guy has to be what? The rotor speed. Yep. It's always playing catch up. It's always slipping is the term we use, right? The rotor speed electrically is always less than the field rotational speed. All right, omega is greater than omega m times p over 2. Okay. He's always slipping a little bit behind. Okay. All right. So those are our core differences, right? So real quick, just to summarize here, if I look at the synchronous machine, okay, in the case of the synchronous machine, these are our core quantities that I have here. I got a DC current in the field coil. Those are all my time domain quantities. Those are my phasor quantities, okay? I said that the rotor has a mechanical position that I defined there, theta r, okay? And basically says that the position of the rotor, the angle of the rotor is changing over time. Now, this value right here, theta naught, right? What is theta naught? The initial position. And it's not really just the initial position like a t equal to 0, but it's the initial position at the beginning of every rotation. So when he gets to the end of one rotation, he's back at the same spot every time. Now that's particularly important because in the case of the way the synchronous machine works, right? We derived the circuit model for this thing. This is the circuit model that we use, all right? Now, from my perspective, basically, so looking at this here, I've put one winding of this machine. This is a three-phase machine, so it's one of three windings. All right. EAF and LD and VA. VA is the grid, right? EAF and LD, those are inside the machine. Okay. That's our sort of model for the machine. Now, looking at this, basically if I step back, and I don't want to get too lost in the weeds here, but basically what happens is LD and EAF together, when this thing is connected to the grid, basically act like a current source. Right? The grid voltage is fixed. And if I need to push more power into the grid, I sub A changes to make sure that I push more power into the grid. Right? If I want to push more power, P, into the grid, what do I have to do to push more power into the grid? Change what? Change the torque, which means I need to push, basically I need to increase the loading on the turbine. So somehow I need to get more steam or more combustion happening inside if it's a gas turbine. I need to actually do more energy conversion. I need to get more energy out of the coal or out of the nuclear process or out of the gas to be able to push more power into the grid and change the current. Now, when that happens, in terms of this circuit model, what changes? The current's going to change, right? But what changes about what the machine does? The current is just a result of its configuration from KVL here. If I push more power into the turbine, I'm going to push more power into the grid. What changes in this circuit model when that happens?
Is it more current?
Yeah, there's more current that ends up flowing, right? It's that delta angle that changes. Basically, where that EAF voltage is relative to the grid voltage is what changes. All right? That delta value there. So what that means is basically that the speed of the motor for a short period of time, the speed of the motor changes to basically push the field winding a little bit further ahead during its rotation. All right? So the rotor kind of moves forward a little bit or backward, depending on the situation. Okay. That's basically what's happening is they move in synchronism with each other. During a transient, it speeds up or it slows down, and it settles out at a new value of theta naught, which is related to that delta value. All right. It's a basic principle to sort of understand that it's really fundamental that thing operates in synchronism with the grid. All right. When we talk about issues of the grid being unstable, that's really when it comes down to a situation where those machines are losing synchronism with the grid, which can happen. All right. Typically, it happens because there's a short circuit or there's some sort of funny phenomenon that's going on the grid side. Okay. And you're looking at that in problem one. So one picture that we need to just kind of understand real quick about that synchronous machine is that picture right there in the upper right. What I've shown there is the power curve. All right, so we derive this, and this is in summary there in the notes. Basically, the electrical power and the Q that can come out of the terminals of that machine, right? They are related to this angle delta. And if I plot it here, PE, the electrical power out of the machine, all right, where it's positive, this thing is a generator. Where it's negative, it's a motor. All right. And that's a little bit different than the way you're normally taught to think about power. If you go back to what you learned in circuits 1 when you talked about power, positive power there was usually a load, negative power was a generator. Why is it different here? Why is power positive? What am I doing that's kind of counter to our currents coming out of it, right? I basically treated this guy using sort of the opposite of my passive sign convention. It's an active sign convention, but I'm doing it that way because he's a generator. All right, so positive power means he's producing it. All right, so essentially here what I've done is shown that there is a maximum amount of power I can get out of this thing, and I'm showing the power as a function of delta. Okay, power goes negative, nothing wrong with that. Power goes negative, then basically it is a situation where it's a motor. Okay. All right. So there is a maximum amount of power that's going to come out of this thing. What angle delta would be the maximum amount of power? 90 degrees. All right, 90 degrees. Now, in steady state, what's supposed to be true about the mechanical power going into the generator and the electrical power coming out? They're equal. Steady state, those two things better be equal to each other. So the way we can kind of visualize that is this intersection point on the curve, right? So my mechanical power and then my electrical power, this is PE of delta. And this is the mechanical power. In steady state, these guys align with each other. And there is this operating point. And I can call this here delta op. That's where I operate. Now, if I increase the power on the machine, let's say I increased it to here, what's going to happen to the angle delta? It's going to get bigger, right? And that means that rotor is going to spin forward a little bit. All right. What happens if I put mechanical power here? It's an unstable system, right? I'm going to have PM greater than PE, right? Which also means that torque electrical is greater than torque mechanical is greater than torque electrical. What's that going to do? You say it's unstable. What does that mean? What would happen in that case? Well, it will tear itself up. Yeah, it will, right? What's going to happen is I look at J d omega m by dt, Newton's law, right? Tm minus Te. If Tm goes greater than what Te can ever be, in other words, if I go past this point, what's true about the machine's speed? It's going to increase, right? And it's got no way to stop increasing, all right? Not only that, what's worse is as omega m increases, delta is also changing. So it's going to go through these kind of wild motions of essentially pushing more, absorbing more power than, producing more power than absorbing it, and then producing it and absorbing it. It's going to be wild, okay? It's going to be pretty destructive. That is a very unlikely scenario to occur in the real world. That I don't even know that you could really do it unless you had some kind of really serious malfunction.
Yeah.
I'm sure you could have it happen. What I've heard of happening is situations where when you connect the machine to the grid, the synchronism is not correct. All right, and if that's the case, then you can get into some funny situations. The more likely thing to have happen is that I have a short on the grid, right? At the terminals of the machine, if the grid shorts, then this curve moves, right? So in other words, this curve, which is proportional to the grid voltage and this impedance, if the grid voltage changes because there's a short circuit on the grid, then this curve moves itself. That's the situation that you more frequently worry about. And that can get into a situation that leads to instability as well. And that's a lot of protection design is associated with that kind of stuff. If I get a short circuit, I got to be able to deal with making sure that I don't lose synchronism. Okay. All right. Those are all kind of advanced concepts, but the basic idea is important. To think about how this guy operates in steady state, it's basically just kind of determining where does the mechanical power and electrical power meet, and what's the angle delta that's required to hit it. Okay. The induction machine is different. All right. Typically, again, like I said, he operates as a motor. Doesn't have to. Could operate as a generator. All right. But in this particular case, hook it up to a three-phase voltage source, get a three-phase set of currents. That induces a three-phase set of currents on the rotor, right? I don't put them in, I induce them. And then we determined last time a whole set of speed values that are associated with this guy. All right, and all those speed values are important. So you got a mechanical speed, right? That's the speed at which the rotor is rotating. The rotor has what we call an electrical speed, right? Which is basically to say that How fast is the field that rotor is creating? How fast is that moving? I don't need to worry about the details of it, but basically it's P over 2 times the speed that it's moving at. All right. The rotor current frequency. The heck is that? The rotor current frequency. There's an equation for it. I don't like equations. What's it mean to say the rotor current frequency is that? The frequency of the current that's being induced in the rotor, right? So what we said is at 0 speed, when that guy is just, the rotor is sort of locked in space and there's a 60 hertz field moving over it, what would we expect the frequency of the current induced in the rotor to be? 60 hertz. If the rotor gets to full speed, then we know the rotor and the field are moving at the same speed and there's no current induced in it, right? So we get a frequency of 0. All right. So what we defined last time, I defined this quantity slip, right? Which is sort of a rate of, it's telling me fractionally how far behind is the rotor from its full speed. Okay. How far behind is the rotor from full speed? The full speed that the rotor can operate at is called the synchronous speed. All right. And so I've defined it here, omega divided by P over 2. And again, omega means that we're talking radians per second. We typically are talking in RPMs. So if I've got a 2-pole machine, what's the synchronous speed of a 2-pole machine hooked up to a 60 hertz grid? 60 hertz or 3,600 RPM. If I had a 4-pole machine, it would be 30 hertz or 1,800 RPM, right? And I could keep going from there, right? So, all right, those are the basic sort of principles. And then we started talking about how this guy operates last time. We're gonna go through some examples here today. All right, but I want to talk about, well, how this guy sort of behaves when I have it kind of in the real world. So this is our relationship here, our Newton's law relationship. Newton's which law? Second law. Okay. All right. So the net torque is equal to the rate of change of speed times the moment of inertia. All right. So there's two types of loads that we typically deal with, right? A centrifugal load or a positive displacement load. All right. That would be this. Oop. TE is the torque produced by the motor. So this is the torque produced, the electrical torque. And this is the torque required. Now what I notice is that this, okay, so this is torque here, and this is torque here. So this is torque, and this is torque. Any idea what I mean when I say a centrifugal load? The heck is a centrifugal load? No. So basically this guy right here, we're talking about like the actual applications of this thing right here. So if I'm talking about industrial applications or commercial applications, yeah, perfect. This is a pump or a fan. All right. And what I see is that the power, and this is a really important point because I'm going to talk about motor drives a little bit, not today, but in the future. The torque mechanical is some constant times speed squared, roughly. All right, that's not exactly perfect, but it's about right. This positive displacement load, this would be, and I don't expect you guys to necessarily know this, this would be like a compressor. All right, we're going to look at an example of that on Wednesday, like an air compressor. All right, so what's going on is the torque is constant. All right, so those are the sorts of things that we're going to deal with. Is when I look at the way the motor behaves in steady state, where the motor behaves in steady state is where these two things become equal to each other. Okay, where they become equal to each other in steady state and the speed gets itself to be constant. If the torque increases on the load side, then the motor slows down, finds a new happy operating point. All right, we're going to look at that case a little bit as we go through today. All right. All right. So how does this thing work? I went through real quick. I don't want to derive it, but basically, if I look at this thing, there's 6 windings. So if I look at the fluxes in each of the windings, they're ugly, 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 right? How many terms am I going to have here? So if I look at flux, the lambda AS, the flux linking the A phase coil, how many fluxes go through there? 6. 1 self flux from the A phase current, and then 5 mutual fluxes, all right, from basically two from the other rotor coil, or 2 from the other stator coils, and 3 from the rotor coil. Big mess, all right? If I talk about what's going to be in the electrical circuit model, what should be in the electrical circuit model? I'm inducing a current in the rotor. If I'm inducing a current in the rotor, what has to be in that model? Well, I could have something like that, yeah. Let's just remind ourselves again. If I took a transformer like this, and I put another coil on the other side, right? If I put a current into this winding, there's going to be a flux going through the coil or through the core. What's that going to do over here? Going to induce a voltage. Inside this thing is a transformer, right? Basically what's going on is the induction machine is just like a transformer whose secondary is rotating. All right, basically that's all that's happening. All right, and so what we get is basically something that looks like this, right? I kind of derived this out sort of notionally last time. And so I've got in this model, so this is basically for a single phase, for phase A, right? I'm saying I put a voltage on phase A. I also put it on B and C, but I'm only looking at one phase of this thing right now. The frequency on this guy is 2 pi 60. Okay. What's the frequency over here on the rotor side? Is it also 2 pi 60? No, it's different, right? I don't expect anybody to necessarily remember that. It's omega minus P over 2 times omega M. Now, this is sort of a Yahoo problem that I've got here, right? So I want to do impedance analysis because I don't like differential equations, right? If I want to do impedance analysis, can I do impedance analysis? I can. Fundamentally, no, you're right, I can, right? What we showed last time is I basically can make it so that the frequency over here, I can rewrite it as a function of slip, right? I basically said that if I remember that slip is equal to omega minus P over 2 times omega M over omega. If I used that, again, that's in the notes. I don't want to go through that all that carefully. Basically, I can rewrite this guy like so. So basically what I've got that's different here is I have this resistance that's a function of slip. So the resistance of that thing is a function of the speed of the machine. All right, and S, the slip, is omega minus P over 2 times omega M over omega, like that. So this resistor is a function of speed. All right. Now, the other thing about this is, and I showed you that picture of the rotor coil, right? This is what a real rotor coil looks like here. Do I actually have a voltage source that's connected to that rotor? No, it's short-circuited, right? So the difference here on my transformer is there's a short circuit here, and then I refer all this stuff over to the primary. Now, how do I refer stuff over to the primary? What do I have to do to refer things from a secondary to a primary? Multiply by a turns ratio squared, right? Multiply by a turns ratio squared. Now, what is that turns ratio? Nobody knows. No one, you don't go to an induction machine, the handbook, and find what's RS, L leakage. They don't give you those numbers, right? Those numbers are derived doing like open circuit and short circuit tests like we talked about for the transformers. If we really need them, we can get them. All right, we're going to look here in a second at the data I really get on a motor. which is really just its performance information, not its circuit parameters. Okay. All right. This is what the full induction machine model ultimately looks like. Once I refer that stuff over, all right, I get something that looks like this. Now, I'm going to talk about that for a second here real quick, but I want to make sure everybody's remembering a little bit. What is this term? L sub LS? And what is this guy here, LM? What are those things in a transformer? Leakage and magnetizing inductance. All right. Leakage and magnetizing inductance. Which one's going to be bigger? Magnetizing inductance is usually a lot bigger. All right. Usually it's bigger by, almost usually leakage is on the order of 1 to 2% of the magnetizing. Okay. All right. So we've got that. And this is what the referred model looks like. And this is the model everybody uses when they do analysis. All right. Is this simple single phase model. All right. Now, I have no way on earth to measure I2. All right. I2 is, where is I2? Yeah, it's flowing in the rotor and it's referred to the stator. It is not, you can't measure that. There's no way of ever measuring that current. All right. I can measure IAS because that's the current going into the machine. All right. But I can never measure that rotor side current. There's no way to do that on a real machine because I don't have access to it. It's rotating around and it's in these bars anyway, right? So from this, we were able to sort of derive out some basic stuff, all right? In terms of what I care about, in terms of using and designing, if you have to design a problem, so this is a classic senior design thing, your mechanical team is going to tell you, I need this much power. So you might need to do some design on that. So what I care about is what kind of power production and torque production is this guy going to give me? So what I did last time is I was trying to figure out what that power was that I could get out of this thing. So typically this guy is a 3-phase machine. All right. So if I want to talk about the power that is coming out of this thing, what I talk about first is the power that crosses the air gaps. In other words, what's the power that goes one direction? What's the power that transfers basically across the transformer? That's what I call the air gap power. All right. And in problems 2 and problems 3 on the homework, I ask you about the air gap power. All right. The air gap power is the power that goes into this guy right here, crosses the air gap. Okay. So how do I calculate? So in this case, it would be the power that is flowing here in this branch. If I talk about power, air gap power, the power crossing the air gap, what would that be here? How would I calculate that? How would I calculate the power in this branch that I've circled? Which is back to our basics of I2 squared times R2 over S, right? So this guy would be in a single phase, so it's specifically the magnitude of I2 squared times R2 over S. All right. And that would be multiplied by 3 because this is one phase of a 3-phase machine. Okay, so it's 3 times that. And there's a Q that goes with this as well, right? Q, if I wanted to figure out Q across the air gap, it would be the same thing, except it would be times X2 instead of R2 over S. Now, there are 2 components to the power that crosses the air gap. One is the actual power that goes to the load. I read it as P sub M, the actual mechanical power going to the shaft of the machine. That power is going into actually turning a pump or turning a set of fan blades or whatever, right? There is that plus the power of heating. Basically the loss there's a current flowing in the rotor, right? So there's an I squared R that's happening there, right? So I can figure out what that is. That would ultimately be 3 times. Actually, what do you think the heating would be? What do you think the formula would be for this guy, for these? Yep, 3 times I2 squared R2. Okay. And then if I want to figure out what the mechanical power is, I can use those two things together. And I basically get that it's 3 times I2 squared R2 times 1 minus S over S, like that. Right? Yes. Okay. Now, the other thing that we often care about is what's the torque. So if I know the power here, that's good. This is the power transferred to the shaft. How would I relate that power transferred to the shaft? How would I relate that to a torque? What's that? Divided by the speed. So yeah, it's the torque times the mechanical speed. All right. And if I do all that and I rearrange a couple of things, basically the result that I end up getting is the torque electrical is 3 times P over 2 times I2 squared R2 over S, like that. All right. And there's the summary of that. Oh, and there's 3 over omega, like that. All right. So these are our kind of key relationships for performance of this thing. All right. Now, again, no one ever knows what R1, X1, XM, X2, R2 are. And they are a pain to define because the reality of this motor is it's the basic principles that we deal with in a linear circuit analysis aren't quite right. Because what's happening to the machine? Well, it's saturating and all that kind of stuff. And these resistances are very small. All right. These resistances are less than an ohm. If I have a resistor that's less than 1 ohm, it's very sensitive to heating. What happens if a resistor gets hotter? Well, its resistance increases as it gets hotter. Yeah. And so that resistance is really sensitive to temperature. If I just start a motor and let it run for a while, I'll see the current kind of decline over time because the resistances are starting to change inside the machine. Even if it's doing nothing, right? It'll just change a little bit over time. All right. But nonetheless, in the problems I'm giving you, I give you a set of resistances and you guys are playing with the way it behaves. What I typically care about is the information that I get on a motor nameplate. All right, so I'm going to go back to this nameplate picture for a minute. All right, here's an example. This is in a plant. So when I missed class back at the beginning of February, this is where I was. Right, so this is in well, let me ask you, what is that? That's the motor in the back. What's this thing up here? Any ideas? Pump, right? Yeah, it's basically what happens. A centrifugal pump is what that is. And so it's pushing water. This is actually specifically inside of what I call an air washer. This is an old textile mill, right? And what they're doing here is they're pushing air through the building. And this guy is pumping water through a set of coils that are going to cool it off. All right. And so this is a sort of typical sort of operation of what I have. So the motor is on the back, the pump is here. And then if you look at that picture here, I didn't have a great picture of it, but these things are always tough to read anyway, because they're usually pretty rusted out. This is what I call the motor nameplate, that little thing on the side right there. All right, so if you go look at the motor nameplate, what it has is information like what I have right here. All right, so a couple of things that I see. There's a lot of stuff which is maybe, well, it is important, but it's not the stuff that we usually look at. So the frame type, there's a common set of frames that a motor has. The important stuff for me is like this right here. That's the power rating. Any motor sold in the US is going to be in horsepower. If it's sold in Europe, it's going to be in kilowatts. All right. But in the US, it's always going to be stamped with a horsepower rating. And there's a standard set of horsepowers that's defined. If you need to know it, it would be a NEMA motor generator 1. That's the specification. NEMA MG1 tells you what all the standard motor ratings are. Okay. In this case, what I'm looking at is a 25 horsepower motor, which is rated for 230/460 volts. All right. So something's a little bit strange. That's 460. First of all, the motor rating is always in line to line voltage. All right. Now, 460 is a different number than I typically use, right? What number do I typically use for line to line when I give you guys problems? 480. All right. The reason they do this in NEMA MG1, they rate it at 460 volts. Now, you may also have heard before about, sometimes they talk about things being 110 volts, sometimes it's 120 volts, right? That basically for motor ratings, they use a value a little bit lower than what the actual grid is likely to be, because I know the grid's going to fluctuate around. Why would you do that? Why do they rate the motor at a voltage lower than what the grid is likely to be at? Well, so if there's voltage drop on the lines, if I need to provide 25 horsepower no matter what at the output of the machine, and the voltage drops on the lines, what's going to happen as a result? My current's actually going to go up, right? So if I need to provide 25 horsepower at 460 volts or 480 volts, the current's going to be higher at 460 than it is at 480, right? So, and that's why they do it. And basically, you know, if you go into sort of analysis, they do this a lot for nuclear power plants in particular, right? They worry about what's going to happen if the voltage starts to get too low. Is this guy going to start to misbehave? Is he going to be able to produce the right amount of torque? So the standards are very clear about what values of voltage they rate them at. All right. Now it also tells me here that his rated RPM is 1750 RPM. All right. How many poles do you think this thing has? 4. With 4 poles, what would be his full speed? 1800 RPM. Okay. That would be his full speed. When he's operating at rated speed, he's at 1750. Only 15 RPM or 50 RPM different. He's slipping a little bit, but he's not slipping much. All right, at rated operation. And then there's a bunch of other stuff on here that's important, which I'm not going to get into as much. Things like the efficiency of this guy and certain other aspects. All right, which I'm happy to talk about if you got questions, but kind of beyond what we need to worry about. All right. All right. Now, what I talk about is a couple of curves here. So this is sort of standard stuff. So I plot the torque and the current versus speed. All right. So the torque curve is this guy per unit torque. And oftentimes people do this in terms of per unit, because if I have 2 motors, right? 2 motors, one of them could be producing, 1,000 Newton meters and the other one 100 Newton meters. They're gonna have totally different torques. Their curve's gonna look the same. At 100% torque, 100% of its rated torque is where he's supposed to be operating, independent of whatever torque he produces. 1 per unit torque. So if I look at this, right, basically this guy right here, this variable torque load, this would basically be a pump or a fan. That dashed line is basically the load torque. Where that dashed line and this curve intersect, that guy is where this guy operates. This point right here is my operating point.
Speed.
Well, yeah, so it's producing that much torque at whatever that speed is. So oftentimes that speed is just a couple of percent lower than his full speed. All right. And so what I can also see here is the motor current versus speed. So the motor current, if I look at the motor current, right, here's where he's operating. The motor current somewhere around here. All right. So in other words, the motor current at my operating point, if I look at this, right, the operating point is where these two, the load, so TE equals T mechanical. And if I guess I can think of this as TE and this is TM right here. Right? Where those intersect, that's my operating point. If I look at my current curve, it looks like it's at this particular point, this particular speed, my current's down here. So I'm at 100% current when my torque is at 100%. All right, that's the basic operating principle of this thing. Okay. Now, what do you notice about the current as my speed decreases? So as my speed goes towards 0, what do you notice about that? Goes way up. In fact, it typically goes to about 6 times its rated current. And that's not a hard and fast rule. I've seen it as much as 10 to 12. It depends on how hot the motor is, depends on a whole bunch of stuff, but usually it's on the order of about 6 times. All right, now where does that come from? All right, we're gonna do an example here to think about where that comes from. So here's the example that I have. This motor is a 500 horsepower motor, and it's got 2300 volts line to line. Those are the parameters, and it's rated to operate at 1773 RPM. All right, so that's his rated condition. All right, so I want to understand, here's my basic approach to this thing, because this is the question you guys are going to ask. I ask you to do some analysis with this stuff in the homework.
Number 2.
Yeah, it's similar to number 2 and number 3, really. If I'm looking at this and I want to figure out what the torque production is going to be. The torque supposedly is, right, torque electrical is supposedly 3 over omega times P over 2 times, what is it? I2 squared times R2 over S. Okay. If I asked you to plot the torque versus the slip or versus the speed, how would you do that? What do I have to know? According to this, I mean, omega is a constant, P is a constant, R2 is a constant. So what? I got to figure out the current, I2, right? How would I figure out that current? So let's remind ourselves, right? So I show it like this, but I'm going to hook this guy up to a voltage source, VAS. All right. Now, VAS, I was told that I had 2300 volts line to line right there. Okay, so what is VAS? 2300 over root 3, right? Because I'm looking at, so AS is essentially for the line to neutral voltage here. Yeah, this is a line to neutral circuit. Okay. Now, how can I find I2? That's correct. Circuit analysis, yes. Choose your favorite methodology here. KCL and KVL. Oh, it's very general, yeah. What'd you say? V over Z. That is the way I'd like to approach this. V over Z. Or I was expecting somebody to say meshes or something. It'd be get kind of nasty. It's not nasty, but it is kind of nasty actually. All right. What's Z here in this case?
Combination of those others.
R1 plus JX1. Yep.
Parallel combination of X2 and XM.
Yep. In series with the. Yep. In this combination here, in parallel with JX2 plus R2 over S. Okay. So let's just dive into this for a second. So in problem 3 in particular, S is a vector, right? Where I tell you that S is going to be a set of numbers. Slip is between 0 and 1. So it's going to be a set of numbers between 0. Let's just say I write it like this. All right. So S is going to be a vector. Now, if I look at something like this guy right here, right? This guy is gonna end up being J times XM, right? If this is Z1 and this is Z2 in parallel, what's the formula for Z1 in parallel with Z2? Yeah, product over the sum. Yeah, so this guy's gonna become JXM times JX2 plus R2 over S all over JXM plus JX2 plus R2 over S. Now, just a quick hint, right? This stuff's going to be in MATLAB with vectors. So R2 over S, can I just write R2 divided by S? No. You got to remember to do R2 dot divide S. Right? And then this whole thing down here, you're gonna have to do the top dot divided by whatever's on the bottom, right? You have to be careful about that stuff. All right. So the current, so I have Z and I have VAS. What current's that going to tell me? IAS, the stator side current. Yep. VAS divided by Z. Now the current that I want is not IAS necessarily, right? I want to know the torque. What current do I want to know? I2. So how could I get that? Current dividers. Well, so current divider is the easiest way for me to think of it, right? If I know what IAS is, I have that current dividing between XM and that branch. All right, so I'll let you go into the current divider relationship to remember that, but that's what I would recommend that you do. Use the current divider relationship to figure out I2. All right, now intuitively, what's going to happen here? Let's think about this. Startup and full load. I want to skip the full load first. At full load, actually, I want to say not full load, but I want to say it this way. I want to say at no load, full speed. Okay, at no load, full speed. How much current do I have in the rotor at that point? If I'm at full speed, no current in the rotor. How fast is the rotor spinning? Maximum speed, 60 hertz. What's the slip at that point? So omega minus P over 2 times omega M over omega. This case, there is no slip. S is 0, right? S is 0. So if that's the case, what's true about this R2 over S? In fact, it's infinite. And that makes sense because there's no current in the rotor, right, in that condition. So I've got an open circuit condition. That means all my current's going through this path right here. All right. Now, if I was at startup, what's my speed at startup? Yeah, my speed is 0. So omega M is equal to 0 at startup. And my slip, which is omega minus P over 2 times omega M over omega, is going to be what? 1. It's 100% slip. It's 100% off from rated speed. So now R2 is equal to, or R2 over S is just equal to R2, right? So basically what I've done is I put a branch in parallel with XM. Now, if we look at the two conditions here, XM 54 ohms, R2 and X2 much, much smaller than that. Okay. Which one is going to draw more current from the grid? In the case where I have these two parallel branches, or in the case where this branch is an open circuit? Which one pulls more current? The one's going to pull more current is at startup, when I have basically a very low impedance in parallel with a big impedance. Low impedance in parallel with big impedance is what? Low impedance. All right. So in other words, the total series impedance is going to be intuitively in that case a lot bigger. Or sorry, a lot smaller, meaning the current's going to be a lot bigger. Okay. So here's how that kind of manifests itself. All right. This is what, if I take an oscilloscope and I measure the current as a function of time as the motor starts up, it looks like this. All right. Now I'm going to show you on Wednesday. We don't typically look at, this is the full 60 hertz current. Usually what we look at is just the amplitude of the current. All right. If I'm looking at this, here is the startup period. All right. Out there is once I get into the steady state. All right. And this is with no load on the motor. All right. So if I have no load on the motor, I still have current in steady state, right? What's that current? Where's that current going, right? That's not going into any useful work at that point. Where's it going? Well, it's going into XM. It's going into the magnetizing inductance, okay? And so if I look at the way this guy behaves, I want to look at the startup period for a second here. I look at the startup period with no load, what I've got there is IAS. That's what the current looks like. So it's got this big period here that I call an inrush. And as a result of that inrush current, this is what the torque on the machine looks like. What's happening here? The torque is big, and eventually in steady state with no load, the torque is equal to 0. Yeah, this is with no load, so he gets to max speed in steady state. But during this period right here in the transient, what's happening there?
It's taking a lot of current to start it to spin that rotor, right?
Yeah, it's taking a lot of current to start it, to spin the rotor up. And what's going on is I have this situation here, TE minus TM. Basically, TE is real big to get the speed to increase. The inrush current is basically going in to speed up the rotor to full speed. Once I get to full speed, these guys become equal to each other, all right? Which, if there's no load, these are both equal to 0. And so I can see that during that inrush period, the speed is increasing. And in this particular case, it gets to 1800 RPM. Now, I did this in simulation, so I can look at the rotor current. This is what the rotor current looks like, right? By the time I get to steady state, how much current do I have there in the rotor? 0. There's nothing there. Now I put him under full load, okay? To just compare, if I look at steady state, look at the current in steady state versus the current at no load. Which one's more? The full load, right? There should be more current because I have more current going into that, right? At no load, there's no current in this branch. At full load, there is current in that branch, right? So there's going to be more current flowing into the terminals of the machine. One thing I'll notice real quick is if I look at that inrush period, they aren't all that much different though. During the inrush period, all right, it's basically pulling the same amount of current. Once it gets into steady state, it's different. Okay. Now, if I look carefully at what's going on in those particular cases, right? So here's the ramp up of the speed. Here's what the torque looks like. Now the torque in this case is not 0. In this case, it works out to be, I don't know if I have it written down. I think it's roughly about 1900 Newton meters, something like that. All right. And what do we notice about the speed here? Less than 1800. In fact, it works out to be specifically 1773.3 when I 0.34 RPM. Okay. Now he's slipping a little bit behind, not exactly, but he's slipping a little bit behind. And this is what the rotor current looks like. All right. What should that frequency of the rotor current be? Well, that should be omega minus P over 2 times omega M, right? Which if I do that math, that works out to be about 8887 hertz, right? And you can kind of see if I look at this, that period works out to be about 1.1 seconds. So if you look at my time here, you'll see that works out to be about right, looking at that picture. Very low frequency current. In fact, the weird thing is if I look at the frequency during the startup, the frequency is changing. Over here, this is 60 hertz current. Over here, this is 1.1 hertz current. Exponential change of the frequency, right? That's what's happening as this guy sort of speeds up. Pretty freaking magical. What's kind of going on there. Tesla was a pretty smart guy for this stuff, right? To be able to figure this concept out. All right, now, if one of the things that I ask you about in problem 3 is to generate some curves versus speed. So this is the same thing I was looking at just there on that last sort of introductory slide. Basically, what I'm looking at is for a particular circuit. In this case, I did it for those parameters that I just showed you. What does the current in the machine look like as a function of speed? And it's a function of speed because one of the resistances is a function of speed. Okay, so if I look at this induction machine, so out here at 1800 RPM at full speed, there's very little current. At full, it works out to be about 6 times whatever it is at rated. All right, that's about how this works out. And there's 2 curves here. I2 is the current in the rotor side. IAS is the current coming in off the grid. They're very close to each other, right? IAS off the grid's a little bit higher because there's also current going into that magnetizing branch, right? So there has to be a little bit more current coming in. Now I want to sort of stop here. Basically what I've got is the torque, the air gap power, and the mechanical power. So I want to look at those things real quick here, right? So this guy is rated for, this is the torque right here. This is the torque. This is the air gap power, and this is the mechanical power, right? The power going into the shaft. Now, I said this motor was rated for 500 horsepower, and he was supposed to spin at 1773 RPM at full power. So if I zoom in here, so notice, first of all, this is his rated operating range right there. It's a lot of speeds that we're not using, right, in steady state, at least, right? This is his operating point right there. That's where he's producing full torque, which is about 1900. It's actually close to like 1980 RPM, something like that. Sorry, 1980 Newton meters. So here's where he is. He's supposed to be at 1773 RPM, and that's about where he is, right? Now, if I look at the mechanical power, right, this is what the power looks like, and I'll zoom in on that. So the mechanical power, so this is 500 horsepower. It's saying this guy's at about 1768 RPM. All right. So when we talk about how this guy operates, this is the context in which we operate it. The induction machine is sort of often called a constant speed machine. And the reason we call it a constant speed machine is it's varying from 1800 at no load to 1770. I only changed 30 RPM. That's not a whole lot. All right. If I want it to change its speed, which I often do, then I have to put a drive on that thing. In other words, I have to put some electronics that are going to make the voltage that it's applied change to it. And we're going to look at that. Okay. All right. Stop there for today. All right. And